All right, good morning, everybody. We'll get started in a minute or so. Hot, but good. We're waiting for everybody to show up. Boy, did I have, I had a busy morning. I was out the door by 6:15. I went to Valley shopping, by the way, Tuesday. Seniors get a 10% discount. I think I could qualify. And bought a lot of stuff, about $120, because I just stocked up. I don't think I'll go shopping for the next couple of weeks. But anyways, then brought it all in, put it away, off to physical therapy. Yes, the back is a lot better. And now I'm here. So this has been a real busy morning already, and it should be more exciting. All right, let's get going. Yay, let's get going. All right, good morning, everybody. Welcome to another exciting morning of chemistry with your host, me, Dr. White, and Chem 1211. And a couple things. First of all, I might forget, but I'll do it now so I don't. I'd like to wish everybody a healthy and happy Thanksgiving. Be careful out there. Hopefully you're staying home. I am. And just meet people by Zoom or whatever. And just be safe out there. It's getting dangerous. Saw on the news all those people flying. Hope the best, but I fear the worst for what's going to happen. But that's out of my control. What I can control is what I'm going to do this morning. And I haven't said this in a long time, but I think you guys got the hang of it. Remember, there's no such thing as a dumb question in my class. All right, important things. A week from this Thursday will be test 4. Test 4 will be on equilibrium, which I'm going to go through the problem set today. And then I'll finish up acids and bases today. And I'll go on Tuesday, I'll go through the problem set on acids and bases. I think I might even spend some more time on acids and bases and equilibrium to get you ready for test number 4. Don't tell anybody I'm being nice over my image around here. Shh. Now, I did get an email, and that was that evaluations, electronic evaluations are out for this course. If you want to do it, do it. If you don't, don't. But if you really like what I did this semester, go to ratemyprofessor.com and put something down. If you really didn't like what I did this semester, do the same thing. Now, if you really, really, really liked what I did, send an email to the Board of Trustees, copy the president. And if you're going to do that, don't say, hey, that's not too professional to start your email. Say something like, dear Board of Trustees, or something like that. It's more professional. And if you do go that route, write your letter, let it sit for a day or two, and then send it out. And that way you can look and say, oh, let me change this so it sounds better. So if you really, really like what I did, send an email to the Board of Trustees, copy the president. And if you really, really didn't like what I did, do the same thing. I'm an equal opportunity person. All right, let's get going. We got a lot to do and enough time to do it. Oh, one other thing. Yesterday was a really long day. I had our Thursday lecture yesterday, or actually I had a lecture yesterday for 2 hours. And then I had another 3-hour class at the other school, plus office hour, plus other things. I haven't gotten to the video. I'm running a little behind. By Thursday or Friday, I'll be all caught up for us this week. But I am running a little behind. The other thing that got me behind was I called my internet company and we were able to track down my problem in my basement, which I haven't touched, or they haven't touched in at least 4 years. Last time someone was out, was a slightly loose connection for the cable that comes up to my modem. And once we tightened it, because the guy I was talking to did a good job with me, said your signal from your modem is very low. And we tracked down and it was back up to. I wonder if it'll take care of the clicking. Anybody hear the clicking? You do hear it? All right, I got something else to work on that. Well, at least got one problem. I'm still here. All right, let's do the practice problems for chapter 15, which we skipped 14. Does everybody see chapter 15 on the screen? Thank you. All right, let's do the practice problems. Number 1, name a key factor in the collision theory of reactions that is needed in order for a reaction to occur. You only have to put down one, but I gave all 3. And that's the reactant molecules must collide. That's why it's called the collision theory. Collisions must have enough energy to make a reaction. That's called the activation energy. And the molecules have to have proper orientation. All right, next one. Ooh, what is the activation energy? And you should know that's the amount of energy needed to make a reaction occur. Now, how do you make a reaction go faster? Well, add more reactants, increase the reaction temperature. And another one I could have put down here, which I didn't, is add a catalyst. And lo and behold, there it is. All right, now you should know how to draw an energy diagram. Notice this is exothermic because on the product side, you have the heat. You're giving off heat. And for this reaction, at start, there's a certain amount of energy here of the hydrogen, and the total energy on this side has to equal the total energy on this side. Well, if you lose some heat, this ammonia has to be lower, and it is. And you have the hill, over the hill and down the hill, the grandmother's house we go. And here you should show the activation energy. That's where you start to the top of the hill. And it's called EACT. Next, I have a endothermic reaction. How do you know it's endothermic? Because you have to add heat. It's on the left side. And remember, the total amount of energy on this side equals the amount on this side. Well, if this is water plus heat, the water is going to be less than this side. And again, you go over the hill and down the hill to the products. And the activation energy is where you start to the top of the hill. Now, you should know how to write the equilibrium constant. And the equilibrium constant is the products on top, the concentration to the coefficient power times each other divided by the reactants to the coefficient power. So we have 4 sodium, molar quantity of sodium for power, times. Now, common mistakes students make there, they see this plus and they do something like this. And that's wrong. It even says it on the screen. Oh no, it's Awful Humor Tuesday. And that's how you do it. If we look at this one, same thing. Potassium chloride concentration, the coefficient is 2, so it's the power 2 times the oxygen coefficient, oxygen concentration, coefficient is 3. Remember, it's times, not plus. And this is potassium perchlorate, and to the power of the coefficient. By the way, this also gives off a lot of heat, and potassium perchlorate is one of the chemicals that for many years was used as solid rocket repellent, a propellant by our military. Watch out, Dr. White knows all this stuff. He's real dangerous. And I give some more examples. Now, remember, in the roughest form, K equilibrium is approximately concentration of products divided by concentration of reactants. And here in 7, predict the relative amount of reactants and products. Now, for A, we have this equilibrium, and we're given the equilibrium constant. And notice it's a large number, 10 to the 4th. K equilibrium is much greater than 1. For that to happen, you have to have this number bigger than this number. And therefore, by the way, the 3 dots means therefore. It's the cool way of writing therefore. If you've ever had math or logic, 3 dots. Therefore, products are greater than reactants. That's when equilibrium constant is much greater than 1. Oh, look at this. It's 10 times 10 to the minus 4th. In case you can't see that, I'll take out my magnifying glass. And if you haven't figured that out, that's a very small number. And K equilibrium is much, much less than 1. Therefore, when it's less than 1, you have always more reactants than products. By the way, this means greater than. And here, if you can't see it, I'll take out my magnifying glass as 10 to the 30th, which I hope you all know is much, much greater than 1. Therefore, the product concentration is much greater than the reactants. Finally, let's do the Chatelain's principle. See, I still use my North Side Chicago French accent. Just like I can't roll R's, I don't speak French words that well either. Wait, I take it back. Eiffel Tower, I see I can do some. Croissant, I haven't had a good croissant in a long time. Like I need one, like I need a hole in my head. Now, remember the Chatelain's principle. A equilibrium under stress shifts to the direction to remove the stress. An equilibrium under stress shifts to the direction that removes the stress. I'll never ask you what is the Chatelain's principle, but I'll expect you to know how to use it. All right. Let me real quick. Everybody see problem 8 on the screen? You see it? Thank you. All right. Now, for the following reaction, and it's in equilibrium. Ooh, got a quick question for you. At equilibrium, what can you tell me about the forward and reverse rates of the equilibrium reaction? I'll give you 8.2 seconds to think about it. Go. 7.5, 7 3/4, 8, 8.05, 8.052. Time's up. At equilibrium, by definition, the forward and reverse rates are the same. I'll say that again in slow motion. At equilibrium, the forward and reverse rates are the same. So I can do things in slow motion. Am I cool or what? Not. All right, let's go back to the problem. Now, For the following reaction, I have an equilibrium. What happens to the oxygen and chlorine concentration if you add more water? Well, at equilibrium, there was a certain amount of chlorine, certain amount of water, certain amount of HCl, hydrochloric acid, and a certain amount of oxygen. Well, if you add more water, all of a sudden the equilibrium says, oh no, we've got too much water. How do we get rid of it? The only way you can get rid of it is it reacts with chlorine to make more HCl and water, not water, oxygen. This reacts with this to go this way. Because when something reacts with something else, it's consumed. Ooh, this thought of something. Dr. White was a good boy. I didn't break down and buy his French silk pie this morning for Thanksgiving, which is a good thing, I think. I'll wait till my birthday. But, by the way, my birthday is coming the end of December. Don't forget, my all-time birthday gift is just a mold of pennies. It's just pennies. But anyways, if you have a French silk pie and you consume half of it, how much pie do you have left? More or less than when you started? Less. You have a half instead of a whole one. So whenever you react or consume something, its concentration goes down, which is what we want to do. And therefore, what happens? Too much water, it shifts this way. Therefore, some of the chlorine is reacted. That also is consumed. Therefore, it decreases. When it shifts this way, you make more HCl and more oxygen and make more of something, how much you have will increase. Now, what happens when you add more HCl? At equilibrium, there's a certain amount of HCl. Well, you've added more now. Oh, woe is me. What happens? We've got too much HCl. How can we get rid of HCl? The only way you can do that is by reacting it with oxygen, and the equilibrium is shifted that way. When this reacts with oxygen, oxygen is consumed, and therefore you have less. It decreases. When it reacts with hydrochloric acid, HCl, it goes this way and it makes more chlorine. So that's increased. Now, what happens, part C, if you remove some water? Well, at equilibrium, there was a certain amount of water. We've taken some away. And the equilibrium says, oh no, we need more water. We're low. How can you get more water? Only one way. HCl and oxygen react to make more water and more chlorine. Therefore, if something reacts, the oxygen will be less. If it goes this direction to make more water, it will make more chlorine. That should be more. Ooh, I got it right. Now, let's look at exothermic and endothermic, and something you should remember. When you put something in an ice bath, that removes heat. Ice bath, cold, that means it's removing heat. Boiling water, hot, adds heat. Again, ice bath removes heat. Boiling water adds heat. All right, let's look at number 10. By the way, C6H6 is called benzene. That will never be on a test. And this is called Cyclo Hexane. Dr. White's an organic chemist and knows this stuff. Now, this is an exothermic reaction because we give off heat. Now, what happens to the following of the benzene and cyclohexane if you put it in an ice bath? Well, the ice bath is going to remove heat. At equilibrium, there's a certain amount of heat. Now there's less. And says, oh no, we've got to make more heat. How can it make more heat? Benzene plus hydrogen react to go this way. And it makes more cyclohexane and heat. Well, what happens to the concentration of benzene? Since it's reacting with hydrogen, it's consumed and it will decrease. What happens to C6H12, cyclohexane? Well, you're making more heat. You're going to make more of this also, so the concentration will increase. Now, what happens to the concentration if you put the reaction in a beaker of boiling water? Boiling water adds heat. At equilibrium, there was a certain amount of heat. I just wanted to check. A certain amount of heat. Now you've got too much, and it says, oh no, I've got too much heat. How do I get rid of it? Well, there's too much heat, and the only way you can get rid of it is to react it with the cyclohexane. And that means this is going to be C6H12 consumed. You'll have less. And that's what I have down here. It's decreased. Now, since it's going this way to remove the excess heat, you're going to make more hydrogen, more benzene, C6H6. When you make more of something, the concentration increases. And finally, what happens to those two when you add hydrogen? Well, if you add hydrogen at equilibrium, there's a certain amount of hydrogen. Now there's too much. And the reaction, equilibrium reaction says, oh no, it could also say, woe is me. I have too much hydrogen. I got to get rid of some of it. How does it do that? It shifts the equilibrium this way because benzene reacts with hydrogen to lower the concentration. When something reacts, it's consumed and you have less. I'm going to have less tea now because I'm going to do a tea break. Oh, is that good? I just consumed some tea, so there's less in my glass. But anyways, to get rid of the excess, it goes in this direction. Therefore, if benzene reacts, is consumed, you have less. And this is the benzene, C6H6, there's less. And the cyclohexane, C6H12, you'll make more of it because you're going in this direction, and therefore you'll have more of it. Its concentration will increase. Let's do one more because these are good for your grade. Can't. Ooh, the plus sign disappeared. This is an endothermic reaction. We're adding heat. And what happens to the carbon monoxide and the hydrogen if you put it in an ice bath? Ice bath removes heat. Therefore, at equilibrium, I had a certain amount of heat. Now I have less, and the reaction says, oh no, we need more heat. How does it make more heat? Carbon dioxide and hydrogen react to make more heat, and it will also make more water and carbon monoxide. Therefore, what happens to the concentration of carbon monoxide? Well, you're going to make more heat, you'll make more of that, it increases. If carbon dioxide and hydrogen react to go this way, this is going to get consumed, and guess what? You'll have less. It decreases. Next, what happens if you put the reaction in boiling water? Boiling water adds heat. Therefore, at equilibrium, there's a certain amount of heat, you put it in the boiling water, and oh no, I've got more heat. I've got too much. I've got to get rid of some of the heat. How does it do that? Heat reacts with water and carbon monoxide to go this way to make more CO2 and hydrogen. Well, if this is consumed CO with the heat, I'm going to have less. If this all reacts to make more of this side, I'm going to have more hydrogen. And the hydrogen, oh, I was looking at the wrong one. B, the hydrogen increases and the CO decreases. And finally, if you add more CO2, what happens? I've added more CO2. At equilibrium, there was a certain amount of CO2. Now there's way too much because I've added more CO2. And so the reaction says, oh no, I've got too much CO2. I've got to get rid of it. How do I get rid of the excess CO2 to get back to equilibrium? I react with hydrogen to go this way. I make more heat, more water, more carbon monoxide. Well, if I react the CO2 with hydrogen, this is consumed. There'll be less. Oh, I got it right. Hydrogen decreases, there's less. And the carbon monoxide, which I'm making more heat, and water to get rid of the excess CO2, this should increase because I'm making it. And it does. And that's problem set 15. Any questions? Going once? Going twice? Let's move on. Probably the most important thing I'll teach you this semester is pH. And as we talked about yesterday, pH is minus the log of the hydronium ion concentration. You'll be given this an important information, test number 4. Wow, we're already up to number 4. Oh no, that's sad. The semester's almost over. Everybody else is clapping. No. And remember, my special gift to you is, oops, hold on one second. There, squiggly lines. if the hydronium ion concentration, and this is 1.0 times 10 to the minus x, then the pH is x, because pH minus log 1.0 times 10 to the minus x equals x. And we went through some problems on Tuesday. Now, this is one thing I'm going to expect you to know, and I will not put it in important information. I better be subtle. Hint, hint, wink, wink, say no more. That comes from Monty Python. Dr. White doesn't take credit for other people's great jokes or other things either. pH scale goes 0 to 14. At 7, you have a neutral pH, or neutral solution, really it's called. That's because the hydronium and hydroxide concentration are equal. Below 7, it's acidic, because the hydronium ion concentration is greater than the hydroxide. Above 7 is basic. And that's because the hydroxide is greater than hydronium. Now, the contents of your stomach has a pH of 3. What is the reason, the chemical reason for this class, that the contents of your stomach is about 3? And the answer is, it's acidic. Or you could have also said, there's an acid present in my stomach. Oh no, I've got an acid. Well, it's a good thing that breaks down the food, but that's not the chemical reason I'm asking for. Now, if you look at ammonia hydroxide solution, the pH is about 11. What's the reason? It's a base, or it's basic. So you should know this chart. If I say the pH of a solution is equal to 9.0, is that acidic, basic, or neutral? And time's up, it's greater than 7, so this is basic. The pH of your blood is 7.0. Is that basic, acidic, or neutral? And time's up, it's neutral. And the pH of battery acid, or a solution of H2SO4, oops, sorry about that. Is equal to 1.0. Is that acidic, basic, or neutral? Acidic. Forgot to write here. And you should know this. Now, each number in pH is logarithmic, and this won't be on a test, but that means it's a power of 10. Going from 6 to 7 is a change of 10. Going from 6 to 3 is a change of 1,000 in the hydronium, but the scale works quite well. In fact, on my last patent, I had a claim where my invention was good from 9.5 to 11.5. And someone had a patent that was somewhat similar, but not really the same. They claimed up to 9. And the examiner said, well, 9 and 9.5 are the same. And I said, no. And I had to teach our lawyer, who went to the examiner's boss, and I gave him the information showing him how pH is logarithmic. And that boss said, no, you're right. And that's how helped me get my last patent. So it helps to know your pH. Ooh. Now, if the pH is too high or low, it will irritate your skin. If you're putting hand lotion on, do you want your hands all of a sudden to look red? No. So chemical, or not chemical, but companies that make your cosmetics and your skin lotions, personal care, are very careful to adjust the pH to make it near 7. In fact, I don't know if they still sell it or not. There was a product years ago, it used to be called Proper pH, some sort of skin lotion or cleanser. And that was called proper pH because some of the products in that market would redden your skin. And they learned, oh, let's make it near 7. Duh. Now, I went through some pH. We did pH practice time. Now, in your book, they have you, anybody reading the book? POH, Skip, I've never used that. Ooh, acids and bases, see, and bicarbonates, see the board. Now, when you react the acid and base together, you get what's called the neutralization reaction. You change the concentration and it changes the pH. All right, switch is on, maybe 20 now. Everybody got the message? Now, if you have an acid, HA is an acid, any acid, and you react it with sodium bicarbonate, which you should know the formula of, which is also known as baking powder. You have an equilibrium, which is mostly that way. And what happens is you get a salt, plus you get carbonic acid, which immediately breaks down to CO2 plus water. Now, see the arrow right there next to CO2? That means gas is formed. So if you take an acid and put in sodium bicarbonate, this is called neutralizing some of the acid. And what happens is the pH, when you add base, the pH will increase. Now, remember I told you a long time ago, you learned a lot about me this semester? Now it's time to tell one of my favorite stories. See, I'm smiling already. And back when I was about 5 or 6, the biggest thing going on in our world, especially the United States and Soviet Union, now Russia, was the space race. And the Americans, us, were an evil race or big competition with the Soviets, the communist, evil. They still are, but that's another story. But anyways, to who could get into space first and who could get to the moon first. And therefore, all the toys and anything little kids could think about were rocket ships and space stuff. Well, there was this one candy, and I'm warning, Dr. White's going to do some artwork, so make sure you don't break any ribs laughing too hard, please. But anyways, there was this little candy that had a hollow tube and a cap that had fins, and inside, it was only about this big, inside it was like a penny or two, maybe 2 cents. They had these little dots of candy, like little beads. The candy was the most god-awful stuff you've ever tasted. How could you know that? Well, when a kid got that, the first thing to do, take the cap, take the candy and dump it in a garbage can. What good candy would a little kid dump in a garbage can? Stuff that's awful. Or as someone I knew who was very cute used to get mad and say, ooh, it's awful, awful. And that was really bad. But anyways, this stuff was awful, awful. Well, what my father showed me, and my father was a pharmacist and loved chemistry. I wonder why I became a chemist. Don't know. Was time to laugh. Here's the rocket ship with the little fins. That was the cap. Take the cap off, turn the tube upside down. You have a test tube. And you put in there some baking powder, sodium bicarbonate. Then you put in some vinegar. Vinegar is an acid, acetic acid. Put the cap back on, hold it like this. Here's the thing. And all of a sudden you'd have a chemical reaction and it would make CO2, carbon dioxide, and build up gas and the cap would fly off. It was like having a ship and you just had blast off. And it was cool and you could do it over and over again. Now, warning, do not use all your mother's baking soda up and not tell her. My best friend at the time, and I haven't seen him in decades, I don't even know if he's still alive, but when I was 5 or 6, my best friend was Dickie Gale. I still remember his name. And he did something really bad. He loved that, and he used up all his mother's baking powder. And it was in the evening or somewhere where she could go out to the supermarket. She was going to bake something, no baking powder. Oh, did he catch it? Oh, did he catch it? So never, never use up all your mother's baking powder doing this, or you'll get in trouble big time. Oh, did he? Luckily, my mother knew what my father was doing, so she kept an eye on, do I have enough? And we'll talk more about this reaction later on. Now, when you add a base, the pH will increase. Now, let's look at this reaction again. So what you'll make, and this is sodium acetate, it's a salt. That tastes a little salty like sodium chloride. You make the gas here, how do you know? Arrow up, and you make water. Well, if this is any acid, like citric acid, if you have citric acid in somewhere and you add baking powder, the pH will increase because you've neutralized, consumed some of the acid. And now it's time to tell you a family secret. My father loved to cook. And my mother was a very good cook. My father was a better one. I had 2 sisters. And on Sundays when he could, he told my sisters and mother, out of the kitchen. It's men are cooking this morning. Stay out. And I cook with them. And when I was in college, most of my friends in the fraternity house, they never learned how to cook, and I could cook. And later on, I'm still a good cook. By the way, you know someone who's an organic chemist, a good one, if they say they're a good organic chemist and can't cook, or not a good cook, they're lying to you, because every good organic chemist I've ever met is a good cook. It comes with the territory. So anyways, one of the things, I don't know how he figured out all this, but I think it's part of growing up with certain ethnic group and also parents coming through the Depression. We had a huge deep chest freezer. I have in my house a huge stand-up freezer that I've had for years that's bigger than my regular refrigerator and stocked full, so I can go a couple months without buying stuff, at least 8 weeks or more. But anyways, he would make a couple gallons of spaghetti sauce and we'd freeze in containers take it out, defrost it, and have it for dinner when we wanted it. My mother liked that because it was an easy dinner. And we make meatballs. But anyways, here's what he taught me, his secret. First of all, have you ever made your own spaghetti sauce and it doesn't taste like the stuff at the good restaurants? Why? One, I don't know how he learned this, but add just a pinch of cinnamon. In a 3 gallon, like 3 gallons I'm talking about, no more than a quarter teaspoon, even a little less than that. I had a friend who had like an 8-quart pot. He put in a tablespoon, a teaspoon. The only thing you could taste was cinnamon. Now, the other thing my father did was, and if you look on good recipes now online, you can see them, is in a big 3-gallon pot of tomato sauce. I mean, we made a lot. He would add near the very end about a teaspoon or so of baking powder. And you'd see it bubble a little on top. There'd be a white foam. What that did was neutralize some of the citric acid, raise the pH so it was milder, smoother, and tasted better. Now, I told this story to one of my classes a couple of years ago, and a couple of weeks later, a student came back to me and said, well, thank you for your father's recipe. My father's thank you. I said, oh, that's interesting. Why? Did you like it? He said, yeah, plus it really helped us. And I said, how could it help you? Well, you don't know something. I said, well, tell me if you like. And the student and her father both suffered from what's called acid reflux, where you have problem with the stomach fluids coming up and burning the heck out of your esophagus. In fact, I worked at one company, another manager had it so bad, he had to have an operation to help stop that. I mean, really bad. Well, anyways, they love spaghetti sauce, but spaghetti sauce, because it has tomatoes, which has citric acid, is acidic and it irritates their esophagus. By adding the sodium bicarbonate, guess what? It raised the pH, it was milder and didn't irritate them, and they could have their spaghetti sauce. Now, about the same time, a student of mine who had a grandmother from the old country, and you can pick which part of the world you want to call old country, said, oh my goodness, that explains why my grandmother, when she has an upset stomach, takes a couple of teaspoons of sodium bicarbonate, which neutralizes some of the acid in your stomach. Antacids do the same thing. Except after she does that, she's always burping. Well, yeah, the acid is making CO2 with the sodium bicarbonate, and that gas is going to go somewhere. Burp. And that's true story. Boy, I bet you didn't learn all these neat things you're learning from Dr. White. And that's acids and bicarbonates. And you should know that. Now, a very important, did you get all that? I'm done. I don't have a slide for this. Let's do the following and last. Let's do a couple things. So I've got you trained. I put this on the screen. You all pay attention. Dr. White's sneaky if you haven't figured it out. Can't spell, but that's beside the point. I'm going to go an extra couple minutes. We'll still get your normal break. I'll let you out on time. I'll get you out before midnight. All right, let's look at this. What happens to the numerical value of the pH of a beaker of water at pH 7.0 if you add HCl? Well, you have to know this is an acid. And the pH scale, I'm going to make room on the screen. This you have to know. I will not give it to you. Well, if you add an acid, you're going to make it more acidic. Therefore, the pH will decrease. Now, if you add NaOH, this is a base, and you need to know that. And when you add more base, you make it more basic, and the pH will increase. Add acid, pH decreases. Add base, pH will increase. And why don't you do C and D? What happens to the pH of a numerical value of pH of a beaker of water at 7.0 if you add some NH3 ammonia and H2SO4? Your turn. When you're done, give me a thumbs up. Or you can give me the high sign. By the way, someone shake their head yes or no. Is the clicking still clicking? That's the problem. It's intermittent. If it was a consistent problem, I would know what to trace it down. Next couple days, I just got in some RF chokes to put on some wires. Over Thanksgiving, I'll probably pop them on, see if that helps. I'll do some recording because I can hear it in the recording. Just think, you're in a class with a clicker. Oh, is that awful? Bad, Dr. White. All right, let's do this. What will happen to the numerical value of a beaker of water, the pH, numerical value of pH of a beaker of water if you add ammonia? Ammonia, you should know, is a base. When you add a base, it becomes more basic, and the pH will increase. H2SO4, what is that? Sulfuric acid. It's an acid. And when you add an acid, the pH will decrease. Oops, wrong thing. So the pH will decrease. And therefore, it's important you know from the list I gave you, HCl, HNO, H2SO4, HNO3 are acids. KOH, NaOH, NH3 are bases. Well, with that, I'm going to give you a holiday treat. Let's take an extra minute, come back at, well, actually, I'm not giving you an extra minute. Well, it matters which clock I look at. Come back at 11 o'clock. That's, for those of you with digital watches, 11:00. For those of you with analog, that's when the big hand is on the 12. And with that, I'm going to go stretch. I'll see you in a couple minutes. time to start. Aren't you glad I have that? I am. I've got 3 of them, and they never leave my house here. So the company that made them in West Germany, I found out about a year ago when I wanted to get some from other people, is out of business. Aren't you glad I had lecture yesterday? And by the way, by the end of the week, I'll catch up with the videos. This is the first week I got behind. Part of it was my internet problem and other things, but I'll catch up. By the way, ketchup's acidic because it has vinegar in it. Speaking about things like that, don't forget extra credit project deadline is next week, I believe. Make sure, maybe the 5th, somewhere around, coming up soon. Make sure you send me a copy of your project before it's due. I'll check it. If there's any problems, I'll let you know so you can fix it and you can get your 10 points. Now you know it's really obnoxious humor Monday, Tuesday. All right, let's get back to work. All right, everybody see acid-base titrations on the screen? Good. Now, there's something very useful called acid-base titration. This is a neutralization reaction. And what I mean by that is remember, acid, proton donor, base, this is an acid, this is a base. And when you react the two together, we call this a neutralization reaction. Now, an acid-base titration is a neutralization reaction which a measured volume of an acid or base of known concentration is completely reacted with a measured volume of acid or base with an unknown concentration. And this allows you to determine the unknown concentration very accurately. And in the United States, in chemical companies throughout the United States, thousands of these are done daily. These are used a little more complex, but still it's an acid-base titration for quality control. I was hired at one company, and every morning the QC chemist, quality control chemist, did about 50 titrations. I said, that's not too exciting, it's boring. And I was able to find a company that made what's called auto titrators and allow them to do more challenging things. Plus we got more accurate results. My boss, who was the vice president of technology and the president of the company in the United States, when I went to them with my proposal for his titrator, do we really need to spend $50,000? I said, it'll pay for itself within 3-4 months. And it did. Because of the work those chemists could do other things that helped with the company. So that's an acid-base titration. By this way, the switch is on, it's up to 12. Now, the important thing is you add enough acid or base to the unknown acid or base to get the pH to 7, neutral pH. And at neutral pH, you know that moles of acid are equal to moles of base. How much you add, and I'll show you this in a second. How do we tell that? Well, one way is an indicator. An indicator is a compound that changes color depending on the pH. It's also known as pH indicators. And the most famous of them all, I'll never ask you on test what's the indicator, is phenolphthalein. And phenolphthalein changes color from a clear to a wine color at pH 7.0. You add one more molecule. Once you're at from 6.999 to 7, it changes color. It's beautiful. I wish we were in the lab at school, because you'd be doing a titration or pH uh, neutralization, titration, acid-base titration. Now, this is the structure of phenolphthalein, and it changes color by reacting with the acid. When the acid is no longer there, it changes to another color. And here's another structure. And titrations are used to calculate the molarity of acid or base. Now, key titration points. At neutral pH, you can calculate the moles of known acid or base. Based on the neutralization reaction, you can determine how many moles of an unknown molarity acid or base was present in the volume of the sample of the unknown. So this allows you to determine molarity of what you're trying to do. So if you know the volume of the unknown acid or base and the moles, you can calculate the molarity. I'll show you how to do that in a second. So for titrations, this is important. At pH 7, when the indicator changes, the moles of base equal the moles of acid. This is only true at the end point, and that's when the indicator pH indicator changes color. It's pH practice time. Oh, yay. This is not the best worded one. Probably I'll do better on test. Oops. All right, let's look at this. What is the molarity of a KOH solution if you have to add 134 milliliters of a 2.00 capital M, that's molarity, HCl solution, to 245 milliliters of the KOH solution to make the color change due to the pH indicator? So what are we trying to find? Molarity of KOH. What are we given? We have 245 milliliters of the KOH. What do we also know? We need 134 milliliters of the 2.00 molar HCl solution to make it change. Well, when the color changes, moles acid equals moles base. And here, this you'll be given, what's moles of acid? You can eliminate the thousand, so we can do that. That's milliliters acid times molarity of acid equals milliliters of base times molarity of base. And what we're trying to find in this case, KOH is a base, so we're trying to find that. So how do we proceed? Well, I can put in, I have 134 milliliters of the acid, and the molarity is 2.00 molar HCl. And that equals 245 milliliters times the molarity of KOH, which we're trying to find. Well, how do you solve for KOH? You get it alone on one side. And how do we do that? Well, I got to get rid of 245. Remember, anything divided by itself equals the number 1. So I'll divide this side by 245. And whatever I do to one side, I'll do to the other, 245 milliliters. This cancels out. I'm going to well, first of all, let me do this. Notice milliliters cancel out. We're left with molarity, which is the units we want. Here's size HCl, here will be molarity KOH. I'm going to rewrite this because Dr. White likes to rewrite things like this. You don't have to. And now, you notice 3 significant figures, 3, 3. My answer should be 3. Hold on a second while I write this down so I don't forget it. Let me open this. And now, first of all, quick question. Everybody see the spreadsheet? ABs, thank you. I'll put in there plus 134 times 2.00 divided by 245. And the answer I get there, and that's the 3 significant figures. Keep the 1, keep the 0, keep the 9. The 1 to round off is 3. That's 4 less, drop it. By the way, 10 to the 0 is 1. So this would be 1.09. And that's how you use titrations. Do we? Oh, we got time. Everybody see some equipment on the screen right now? Aren't you glad I asked? How about now? You see things like right over on the right, this fancy equipment. All right, this is called a dosimat. This is a way of doing a titration. What you normally use in a lab is called a burette, and you can control how much you add. These are much more accurate. With this, and this is a control unit, you also automate it. You have stuff going, you're adding into a solution. This is called a magnetic stir. Back about, 15, 20 years ago, these were about 7,000 a piece. I'll bet they're closer to 10,000 a piece. I got hired by this one company to help their QC, different one than the one I told you about. And I looked around and saw they were using technology from the 1900s, burettes. I talked to the president of the company and my boss and said, we should buy these dosomats. How many do you need? 5 or 6. He said, how much are they? 5. You want me to spend 25,000? I said, all right, hold on. Let me call the company that makes them, Metro, and they'll lend us one for a week and we'll see if it makes a difference. And at the end of the week, the president said, buy them because the quality, these things are so accurate, you can measure at 0.001 milliliters. That's a thousandth of a milliliter accuracy if you know how to use them. Dr. White does. And I also knew how to maintain them too, so you don't break them, which if you're not careful, you can't. They're not that sensitive. And this you're adding a liquid, a base or acid to whatever you're titrating here. This has got a magnet and a magnet under here that spins and that agitates it. But anyways, let's have some more fun with titrations. Don't write yet. Hold on, I'm going to do a different variation. All right, and important information, you'll be given this stuff right here. But you got to know when to use it, but today I'll help you out. And the question is, what is the molarity of 125 milliliter HCl solution if it takes 345 milliliters of a 1.01 capital M NaOH solution to neutralize the HCl solution? And at neutralization, you know moles of acid equal moles of base, which means you know milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And why don't you try this one? Go. I bet everybody else is on their planes to not go where they should be going, or they're playing hooky, or they got caught in a snowstorm on the internet. Well, I'm glad I did my lecture yesterday here. Just think all the stuff I've crammed into your brain this semester. Hopefully it wasn't too painful. And when you're done, give me a thumbs up. Oh, by the way, call your congressmen and senators and tell them, if you want to, I shouldn't say this though, that no one's above the law and someone shouldn't be let off the hook. Hint, hint. I'll do that later today. All right, let's do this. I think everybody's done. So at neutralization, you know this, moles of acid equal moles of base, which is milliliters of acid times molarity of acid equal milliliters of base times molarity. Now, we have 345 milliliters oh, got backwards. I was right the first time. 125 milliliters, and the acid we don't know is the molarity HCl. Actually, I'm getting ahead of myself. Hold on. Dr. White just violated Dr. White's first rule of problem solving. Shame on me. What are we trying to find? The molarity of HCl. What are we given? We have 100 and 25 milliliters of the HCl solution. What are we also given? That we have 345 milliliters of NaOH solution, which is a 1.01 molar NaOH solution. And therefore, we know 125 milliliters of acid times the molarity of the acid, HCl, equals the milliliters of base times the molarity of the base. What are we trying to solve for? Molarity. How do we get it on one side? We get rid of the milliliters. So how do we do that? Anything divided by itself equals 1. Therefore, I'm going to divide this side by 125. Whatever I do to one side, I have to do to the other. This cancels out. I'm left with molarity HCl equals 345 milliliters times 1.01 molar NaOH divided by 125 milliliters. Notice this cancels out and I'm left with molarity, which I want. And now I'll go to my calculator. I cheated while you're doing this. I wrote it on a piece of paper so I wouldn't forget. And if I do this and hit enter, the number I get is this. It should be 3 significant figures. I'll give you 3 seconds to round it off to 3 significant figures. Bonus time, I'll give you another 3. Time's up. Keep 2, keep the 7, keep the 8. Use 7 to round off. That would be 5 or greater. That becomes 2.79 times 10 to the 0, which is 1. So the answer here is 2.79 molar HCl. And that's how you do titrations. And on Tuesday, I'll be going through the acid-base chapter 14 problem set. We'll do more of these. All right, we did our, let me ask. Everybody see buffers on the screen? Thank you. I like that very careful thumbs up you just did, Camille. Oh, I'm just playing with everybody. All right, switch is on still. Next thing I'd like to talk to, which I think is the last thing of this chapter, is buffers. And buffers are a very important part of our life and use Le Chatelier principle. And a buffer, and you should know, I won't ask it on test, but I'll show you why you should know it, is a solution that resists major changes in pH. And this is important when small amounts of acid or bases are added to it. Now, I won't ask, excuse me, I'm getting choked up over buffers. Buffers are usually acids, weak acids, or acid conjugate bases of weak acids. I had that there. But the key thing is buffers do not resist change in pH when a small amount of acid or base are added. Ooh, the end. Let's not get there yet. Hold on, don't write this down yet. Forgot something. All right, took me a while to write that, but I'm done writing. Everybody see it on the screen now? Let me translate it for you. Let's do this, 2.c, what happens to a numerical value of the pH of a buffer solution, important to remember, if you add a small amount of dilute solution of NaOH. And a buffer solution, by definition, resists change to pH when you add a small amount of acid or base. This is a base, and the answer is stays the same. Let's look at B. What happens to the pH, numerical value of the pH of a buffer solution if you add a small amount here of dilute solution of an acid? And guess what? It's a buffer solution. It resists change in acid or base, and therefore it stays the same. And that's how you do buffers. Now, your blood's buffered. Didn't think about that, huh? How do you think that your body keeps your blood pH right at about 7? Because it's buffered. Oh my goodness. It's the end of the chapter. Am I good or am I good? Remember, on Tuesday, we will go through the chapter 14, acids, bases, problem set. So I highly recommend all of you do that before Tuesday. And now it's time to go to the lab. So let's get our safety equipment on. Let's go to the lab. Oh, I can get you out on time today. All right, where'd you just go? All right, hang in there. I thought I had the lab. Oh. see something. Nope, I thought I had it open. Sorry about the technical delay. All right, everybody see doing chemistry with food. Unfortunately, it would be fun to do this. All the items that you find in your kitchen or supermarket are chemicals. I bet you didn't think of that. And the food you eat and the ingredients that you use to make various food dishes are composed of atoms and molecules. And the chemistry that you learn and apply in this class can be applied in the kitchen. Now, in this lab, you'll be investigating the acidity or basicity of foods and cooking ingredients. Remember, acid is a proton donor, a base is a proton acceptor. And you can measure the acidity or basicity by measuring the pH. And I can write on here, and remember pH, less than 7 is acidic, and greater than 7 is basic. And here I show you what it is. And therefore, if the pH is greater than the solution is basic, if it's less than 7, it's acidic. Now, one of the things that you can measure pH, it's not super accurate, but it's quite good, is pH paper. And this changes color depending on the pH of the solution. You take a little solution, put it in there, and it'll change color. And here's a YouTube showing you how to use pH paper. Let's take a look at it. All right, everybody see the YouTube on here? They have different solutions here. Yeah, he puts it in and look at it and look at the color. It's near 12. Let's try it again. pH paper puts in there. See how you can see it now? See how it changed color and it's near 12? So that means whenever he dipped it in was pH 12. Now, ooh, look, it turned red. And now that's about pH 1, which means it's very acidic. And that's how you use pH paper. Now, today's lab, you'll be reacting acidic foods with basic food ingredients. And what is the basic acid-base neutralization? You'll be adding bases to acids, and the pH should go up, but I'm not going to tell you. If we were in the lab, I'd say, now you're going to find out if Dr. White's lying to you or not. Now, the first thing is you're going to be using DI water. And deionized water, it's passed through special filters that take ions like sodium, potassium, calcium out of that. Well, it turns out those filters affect the pH of the water. Normally, you think of pH water 7, but the DI water we have is 6.7. So this is an important number you would have measured in the lab by taking a beak of water and sticking the pH paper in there and matching it to the scale. Quick note, one tough problem I had to solve, a company I was at, they're having problems at their plant in Toledo. And one of the problems was the pH of the final product. It wasn't meeting the specification or range it should be. And the first thing I did when I got down there was I asked someone, what's the pH of your water? They didn't know. I said, let's measure it. And it was like 8. It was the worst water in the United States, I think. This was in Toledo in the summer. Turned out in the winter, because there was less stuff in there because of the colder temperature, the pH was closer to 7. Well, that helped me solve the problem. I don't know if you ever heard this, and don't be offended, but a mentor of mine, one of the great mentors, Sid Shapiro, taught me 2 things. One, common sense is not common. It's not. And 2, never assume, because if you do, you'll become the first 3 letters. And people didn't bother looking at the water. Oh, it can't be the water. Well, I'm looking at everything that's used in that reaction in that plant. And that was one of the big problems. Anyways, back to our lab. Now, in this lab, you're going to be using, if we're in the lab at COD, I'd be telling you, be careful. We're going to be using some very, very dangerous chemicals to test. And what you're going to be doing is reacting certain foods with sodium bicarbonate. Remember, NaHCO3. And here's some nice videos. Remember the rocket video? I'll let you watch those on your own. And what you do is take some DI water, add a little of the food, mix it, then measure the pH and observe it. Then add a small amount of baking powder, stir it, observe it, measure the pH, and then do it again, then add a lot. And then put the stuff in a waste beaker. Now, if you want, you can be very careful in a beaker from your chem kit or plastic container in your kitchen sink with your safety goggles on, and don't forget to wear gloves. Put in some vinegar and mix it with baking powder and have fun. Anyways, in this lab, what would we be doing? Oh, how did I get these 2 on the same line? Should be vinegar, orange juice, ketchup, tomato paste, lemon juice, mustard, and Coke. Like I said, very dangerous, especially the tomato paste that stains clothes if you're not careful. And what you'll do is put in some of the baking powder. Well, here's the data already, and you can go back and look at it. You'll need to look at this to answer questions. So the first part, you're using sodium bicarbonate, a base. You do the same thing, except now you use sodium hydroxide. And part of today's lab is you to figure out which one of these is a stronger base. And how can you tell that? By the pH change. And you do the same thing, put whatever you're testing into a beaker, add a little water, measure the pH, then add a small amount of sodium hydroxide solution, a little more, then a lot more, and mix it and watch what happens. And here's the data. And here are the questions. This lab is due a week from this Thursday. because normally we would have done it this Thursday. And guess what? It's time for Dr. White to do you really want me to do gobble, gobble, gobble? Oh, I didn't do that. But anyways, have a happy Turkey Day. Don't get overstuffed, even though when I'd go to our family one, we eat all the food we can, and we do. The turkey isn't the only thing that gets stuffed at our Thanksgiving get-togethers, normal ones, we do. But anyways, have a happy Thanksgiving, be safe, gain gesund. I'll see you on Tuesday. Oh, you got a whole week without Dr. White. Oh, that sounds sad. Don't forget, next Monday, I'll have my office hours if you need me. I will not. Oh, wait. Today is Tuesday. If you need me, I'll have office hours tonight. That's my special holiday schedule. And with that, I'm going to say, have a great Thanksgiving. By the way, you know what the best part of the turkey is? This is Yiddish. It's called the pupik, otherwise known as the tail. You know the thing that's last part over the fence? Our family fights over that. We finally had mutual treaty agreement to cut it up equally. Oh, we had wars over that, and the skin is good too. With that, have a good one, and I'll see you next Tuesday. Bye now. Dr. White signing off from COD North.